Okay, Bismillahirrahmanirrahim. Welcome to this session. Before starting the session, I would like to talk about the exercise you need to cover for the midterm. So from Rocky's book, this is from Rocky's book. This is from the GSP, the book. Rocky's. So chapter 1, almost all the problem. So you have 16 problems. So all of them. Chapter number 2, that actually covers, you need to basically you need to go through all the problems because you will also find the solution online. However, you can restrict yourself up to let's say up to 2.1 to 2.50. So there are 50 problems. And from chapter 3 as well, 51 problem. So 3.1 to 3.51. So those are the exercise. Please go through that. You will get the solution in online. So most of the problems you will find very simple, and from both from the understanding point of view as well as from the solution part as well. Mostly try to understand the thing. Okay, so if any part of the problem is not been understood properly, so we can discuss it in the subsequent classes. Okay, so for the midterm, so when we can conduct the midterm, please propose the time and date. The midterm probably starts for the first year is from 6th of the September. So we can target the 3rd week of the September, not later than the 4th week. Okay, so before the midterm, we can take a break so that you can take the preparation. So what I have planned, so today is the 26th, and then the 2nd September, I will conduct 2 classes on these 2 days. And after that, we can take a break. So the 9th September is one Thursday. On that week, we can take the break, and the next week, we can take the exam. So in between 12 to 18 September, please mark that, 12 to 18 September 2021, try to fix the exam date and the time. Okay, so definitely you probably have other course exam as well, so please make some coordination, so and try to fix that. Okay, so this is all about the midterm, and also the syllabus contains, this is chapter number 1, chapter number 2, and chapter number 3, and all the lectures we have already given. And also it will include the basic filter design and all pass filter that needs to be covered, okay, in the today's lecture, and probably it needs some more time if necessary.
Sir, is it possible to share the book and the solution in the classroom, sir?
Yeah, I have the solution, and as well as probably I have also the soft copy of the book. Yes, okay, I will share that in your Google Class.
Thank you, sir.
Okay, no problem. And okay, we have Aldi is here. How is Aldi? How are you?
Hello, sir. How are you, sir?
Yeah, Alhamdulillah, fine. How's your health?
Alhamdulillah, now I'm getting better. But still, I don't know why it's still weak.
Okay, yeah, that is the side effect
Yeah.
probably.
And I hope everyone here is good.
Yeah, have you tested negative or you are yet to test?
I already test the is negative, but I don't
Okay,
know. My body is still weak.
okay, yeah, you need to test it again, probably after a few days.
Yes, sir.
Okay, yeah, inshallah, you will be okay and everything will be fine.
Thank you.
Okay, no problem. Okay, so in the last class we have covered up to the low pass filter for in case of IIR type low pass filter, where we have also mentioned that we can improve the quality of the filter by changing the pole location. Similarly, it can be done for the high pass filter. Is a similar things. Of course, this is a high pass filter where we are putting this zero location by the numerator, and this is the zero location and the pole locations. We are changing the sign, and previously that was in the right and now this is in the left direction. So probably we have also covered this in the last class. Okay, now if we move to the section that IIR bandpass filter, what we are expecting, of course, from the pole zero point of view, we are expecting the things are very simple in a way. Sometimes this equation looks very ugly or difficult, but the things are very simple. For the bandpass filter, of course, we are expecting the zeros are in these locations, of course, and that is why the equations are like this. You can start with the pole locations, and you can also do it like that. That is all about the pole the zero locations. What about the pole location? If we think about this, of course, if we put the pole here, that actually passes where you are putting the pole, it shows it actually passes the frequency. Whenever you are putting the zeros, it actually blocks that frequency. Whenever you are putting the pole in the imaginary axis, why you are putting it that? Because we want to pass the frequency pi by 2. We want to block pi, we want to block omega equals to 0. So since this is a imaginary pole, that should also come in a pair. So of course we'll get this kind of pair of the poles. Maybe now in the last lecture we have shown that we can change the position of the pole. Maybe the pole location could be here and this. It can be, or we can shift the pole location. So by shifting this pole location to that direction or in the other direction. So whenever you are shifting the pole locations, what does it do? It actually, so there are three cases. Case number one, let's say, this is a case number 2 when the pole is shifted to the left, and this is case number 3 when you are shifting the pole in the right. So if I try to draw the magnitude response, let's say this is from 0 to pi. We need to understand the thing in case number 1, it should be looks like this. So at definitely pi by 2, you are getting the maximum. In case number 2, when it is shifted little bit left, so where you are getting the maximum, definitely at this location. So it is more than pi by 2. So in between pi by 2 and pi, so let's say in this point. So the magnitude response should be looks like this. Okay, so you can shift the magnitude, the center frequency. This is called the center frequency omega 0. Now the center frequency is shifted for the second case. For the third case, it is between pi by 2 and 0. So we can plot the approximate magnitude response, and it should be looks like this. And this is the third omega 0, and this is the previously this is omega 0, the center frequency. So you can find that you need some complex pole to represent the things. Whenever we need the complex pole, definitely there are two poles out there. Of course, there are two poles. So that's why in the denominators, in the denominators as well, that the equation should be second order equation. So let this equation actually give us the solution. Now we can analyze this whole part first of all. So this is our equation for the band pass IIR type filter, and the whole part is basically multiplied with 1 minus alpha divided by 2. How we got this number we have already discussed in the previous section. For the maximum gain 1, so the maximum gain 1, we found that the cos omega 0 is equals to beta, and omega 0 is equals to, from this we can find that omega 0 is equals to cos inverse the beta. How we can find that? We took it and take the amplitude is equals to 1. From there you can find it very easily. Similarly, we got 2 points in case of magnitude response. We got 2 points. One is lower cutoff and another one is higher cutoff. And definitely you can find where are the cutoff values. Now, if you find the cutoff, the amplitude for the cutoff is 1 divided by √2. From that point of view, you can find the cutoff frequency. You'll get the second order equation. From there, you can find the lower cutoff value and the higher cutoff value, where the lower cutoff, if you make the difference between the higher cutoff and the lower cutoff, that is the bandwidth, which is this. This is the bandwidth, and you can derive this. So please derive these equations. Basically, you need to derive this equation in some part of your exam might be. So do it. And from this equation, we can plot the magnitude response and we can analyze the filter. So from the numerator, we can find where are the pole the 0 locations, and this is very simple. And now from the, so this is the magnitude response, approximate magnitude response, generalized, where we can find that according to these two equations, this equation and this equation, what we can find, this omega 0 depends only on the value of beta. If you change the value of beta, basically it will change the value of omega 0. That means it will shift the value of omega 0. On the other hand, if we concentrate on this equation, the second equation, what happens? You have found that this B, that means the bandwidth, only depends on the value of alpha. So the bandwidth depends on the value of alpha. Okay. So what we have learned that we can shift the bandwidth by using alpha, and we can shift this center frequency just by using the beta value. Those are not the pole or the 0. They are not the poles and the zeros. Of course, you can shift the pole locations and the 0 locations with your purpose. But those are the two components. By changing the value of beta and the alpha, you can change the whole characteristics of the filter. So which has been written here. Okay, you can go on through that, and ultimately you can control the quality of the filter, which is omega 0 over the bandwidth. Omega 0 over the bandwidth. How you can control the omega 0? By beta, and you can control the bandwidth by the alpha. So you can control the quality of the filter. The question is, can you find the pole locations? So alpha and the beta, those are the parameters. They are not the pole location. Okay. What are the 0 locations? We have already found that Z is equals to plus minus 1. That is the 0 location. Now we are searching for the pole location. Try to understand this with an example. With an example given that omega 0 is equals to pi by 2. Omega 0, the center frequency is given at pi by 2. Here is 0 and here is pi. And the bandwidth is pi by 4. The bandwidth is pi by 4. So you can find where is the lower cutoff and the higher cutoff. So this is pi by 4. Now we can find the quality of the filter is omega 0 by d, which is 2. Fine. Now from the equation, we have already learned that the beta is equals to cos omega 0. From there, we can find the beta is equals to 0. So in the equation, in this filter design, the beta hasn't have any impact to the equation. So if we can go back to our original equation, you can find that this is our original equation, where if beta is equals to 0, definitely this term doesn't have any impact. Okay, now only we have the alpha term. Okay, so beta is equals to 0 for this given condition. So from the design side, okay, another term is alpha. We need to find the alpha value for finding the pole locations. So we know that the cos B is equals to this. From there, we have given the value of B and we have found this value. The alpha is equals to this, root over plus minus 1. Now, which value of the alpha we should take? That is a question. To find the pole, we already know the equation of the transfer function. Okay, so that is the transfer function. So here our key point is the denominator equation, this equation. As we already know that equation is a second order equation. So we can find that the Z is equals to this, where fortunately the beta is equals to 0. So this is equals to 0 and this beta is equals to 0. It actually given us this simple equation. If beta is equals to 0, in that case we have found the numerator should be looks like this, where beta is equals to 0. So in this case, we are putting the value of alpha, but let the value of alpha is equals to root 2 minus 1. So here we have the alpha value, and from there we can find two of the values here. Okay, and one is plus j twice root over 2 minus 1 over root over, and we can find that this equation. This is for alpha is equals to root over minus 1. There are two options. One is root over plus 1. So at this moment we are assuming that alpha is equals to root 2 minus 1. So we are letting that. So by letting that, we can find that the Z could be like this. These are the pole location. Where are the pole location? If this is the unit circle, root 2 minus 1 is definitely less than 1. So we can write that the pole locations are like this. One is plus j root 2 minus 1 root, which is this one. Another one is minus j root 2 minus 1 root. So this is the other one. Okay, so we have found it, and we can mention that they are acceptable because they are inside the unit circle. As you can understand that for a causal system, the solution is the exterior part of the pole circle, and this exterior consume the unit circle. So that's why this is acceptable. So we can say that alpha should be is equals to root 2 minus 1 and root 2 minus 1, and that is the value of the alpha From there, we can find the value of the z is this one. If alpha is equals to root 2 plus 1, then what happens? Z is equals to root 2 plus 1, which is definitely more than 1, and it gives a unstable situation, and this is not acceptable. So alpha is equals to root 2 plus 1 is not acceptable, and this is how you can find the pole locations. And finally, we have found the pole locations and the zero locations of the all pass filter is for the given condition. As I have already mentioned that you can shift it to the left or the right. That will, it actually controls what? In a circular fashion, if you shift it like that, it actually controls the value of omega 0. Similarly, if you shift it very close to the center or away from that, it also gives you some changes, and that basically depends on the value of alpha, and the alpha controls the bandwidth, the B value, the bandwidth of the filter. So I have already given that online platform to design the filter, to analyze the filter. Please do that with the help of that online platform. Okay. Now for the band stop filter, you can understand where should be the zero location. Where should be the zero location for the band stop filter? Of course, from our experience, you need to stop band stop filter. So you need to stop somewhere else in between 0 to pi. Let's say it is exactly at pi by 2. So where the 0 should be? The 0 should be at this location. Of course, that is a imaginary, in the imaginary axis. Okay. And where should be the pole? The pole should give the pass signal. So the pole should be somewhere else like this. It can be real or it can be imaginary. No problem with that. Okay. It should be very, very close to the value of omega equals to 0 to omega equals to pi. Okay. Let that this is the equation. This is the equation for the band stop filter. You can analyze the thing. So for example, we can find for gain is equals to 0, where the gain is equals to 0 at the stop band. So you can find for gain equals to 0, you can derive that this is the equation, and the band of the filter is equals to cos inverse twice alpha divided by 1 plus alpha. So how could you find that? You can find the equation for omega 1, and you will find the equation for omega 2. Both of this, for both of those, the amplitude is 1 divided by root 2. From there, you can find this band of the filter. Please derive that. Okay. Again, you can find that by changing the value of beta, you can control the omega 0, and by changing the value of alpha, you can control the bandwidth in the similar fashion. Okay, so please do that. Doing this means need to find the 0 location and the pole locations. Okay, so please do that for the understanding. And how to improve the quality of the filter? We have already mentioned that the cascading is one of the options for FIR filter, FIR type. For the IIR type filter, we need to shift the pole and 0 location to control the quality of the filter. As we have already understood that for band pass filter, low pass filter, high pass filter, as well as for the band pass filter, whenever we are cascading it, then the quality of the filter will improve, of course. And we have already mentioned that for the low pass filter, the quality improved like this. For the high pass filter, Let's say this is a low quality high pass filter. The quality is improved like this whenever you are cascading the things. And for the band pass filter, this is a low quality filter. Improving the quality by cascading is possible. However, in case of band stop filter, what we can find, this is the basic band pass filter. If you make the cascading, it looks like this. And unfortunately, for the second case, let me give in a different color. In case of the second one, you can find that the quality, let's say this is the cutoff frequency. Previously, the bandwidth is this, and now the bandwidth is improving. So which shows that the quality of the filter is decreasing. So that's why the cascading is not possible for the band stop filter in case of FIR type filter design. Okay, we have also talked about conventionally, we also talk about the comb filter. This is a special type of filter, and you can say this is very special for suppressing some particular frequency and the harmonics of that filter. Okay, first of all, let me show you the magnitude response of this kind of filter, why this is comb filter. The magnitude response from that, from this magnitude response, you can understand that why this is called the comb filter. Of course, our range of view, it is enough to understand from 0 to pi. This is 0 to pi. We have higher value, lower value, higher value, lower value, something like this. This basically works like a notch filter for a particular frequency. For this example, the omega is equals to pi by 5, and their I should say the harmonics of that multiplied with k, where k is equals to 1, 3, 5, and so on. So that means you can block this frequency, and block this frequency. Let's say in many cases, we have the power line carrier, and for the small signal processing, there is a 50 hertz noise, mostly for very small signal processing like biomedical applications. This 50 hertz makes a huge impact to your original signal. So let's say this is a good ECG signal, but whenever you are not filtering out this 50 hertz, this signal might looks like this. Okay, so the 50 hertz is capturing all the signals. So whenever you are passing through a 50 hertz notch filter, then probably you are getting the good signal. However, still you might get some noises due to the harmonics of this 50 hertz. So from 100, 150, and so on. So that's why this comb filter is much necessary for the filter design, practical filter design application. So now from the equation point of view, how we can design it, very simple. This is the comb filter. This is the comb filter where HZ is a low pass filter, because as you can understand that we have designed like this. So okay, this is the low pass filter. Now HZ is a conventional low pass filter. We have already designed that, and now the comb filter could be designed as HZ, and Z can be replaced as Z to the power L. So now we can get HZ is equals to Z to the power L. This is not minus L, this is only L. So this is 1 plus Z to the power minus L, because we have minus 1 previously. So Z is now changes or converted to the Z to the power L, where L is an integer value. Okay, so this is the equation. From there, we can replace the value of Z. We know the value of Z is equals to e to the power minus j omega. So we can take a common of this, and by using the Euler identity, we can convert this equation. Okay, where we are now what is our target? This is the equation. What is our target? We need to find where we are getting the maxima and where we are getting the minima. Then we can draw the magnitude response. For getting the maxima, of course, the maxima of a filter is equals to 1. So by doing that equation, we can find that at omega is equals to twice pi r divided by L gives the maxima, where r is equals to r. You can find that this is the maxima, this is the maxima, and this is the maxima, where we got the value of r as well. So here, of course, the r is equals to 0 here. Here, twice r is equals to 1, and then this is r equals to 2. So the value of r is from 0 to L minus 1. Similarly, for cos, omega L divided by 2 is equals to 0, where omega is equals to pi by L into k, where I have already mentioned that k is equals to 1, 3, and 5. Okay, by using those two equations, we can find those maximas and we can find those minimas. Try to understand that you shouldn't proceed after pi. Okay, so up to pi is enough. If we proceed more, it might, you can proceed to the infinity, no problem, but we need to restrict up to the pi value. Okay, so here we let that for this diagram, we let that the L is equals to 5. What is the L? You can say the order of the filter. So it depends on the purpose. First of all, you analyze your actual signal in the frequency domain. You should analyze that which frequency and the harmonics are devastating for your signal. Then you can proceed with this example. Okay, so I have already mentioned that 50 Hz rejection and also its harmonics. This is one, and rejection of periodic interference for the telecommunications. There are some interference. Let's say you have this antenna, and this antenna is capturing a lot of signals, and you know that there are some frequency hopping between different channels. If you find the relation that, okay, the interference of channel number 1 to 2 and 3, they have the relation of some frequency, they looks like harmonics, then you can use this kind of comp filter for designing. Okay. Other thing is, if you need the filter design like this, so we have designed the filter like this, isn't it? Like that. But if you want to design the filter like this, you understand the difference. Here it starts with the maximum value. Here it starts with the minimum value. Sometimes you might need that you want to block the DC value and some harmonics, DC value and some harmonics. If it is necessary, then what we can do, we can start with a high pass filter. We can start with the high pass filter. Previously, we start with the HZ. We start with half 1 plus z to the power minus 1, which is a low pass filter. Now we can start with the high pass filter, H. Take H is equals to this, which actually gives you the equation like this. And from there, you can find that the equation in the previous case, the equation actually gives you the cos formula. Now you will find, due to the negative sign, you will get sine formula, and it produces the sine function, which actually gives us this kind of magnitude response. Okay, so that basically solve solve the problem whenever we need the DC value blocking. Okay. Okay. Now we can talk about the all pass filter. Before going to the all pass filter, we need to talk about two particular topic. Probably you understand those things from your previous study period, that what is the group delay and what is the linear and non-linear phase delay, what is the perception of that. This is very important. How you can explain the non-linearity of the phase practically and the group delay practically. What do you know about the group delay, and how the group delay, non-linear group delay and constant group delay helps us to reform or build the original signal back. This is very important. Okay, so first of all, let me discuss it from the mathematical perspective. If we have a linear phase response of a particular system, let that is minus omega nd. Always it's better to write with some example omega into 2. If I write like this, you can write it like minus 2 omega. That is the linear phase, and you can draw it, of course, of the linearity for omega is equals to 0. Omega equals to 0. The phase, this is a phase. The phase is definitely 0. When omega is proceeding higher value, of course, it will goes in the negative fashion. Okay. At omega is equals to pi, what would be the value? That would be minus twice pi. That is the value. Okay. Whatever the case, of course, the omega is increasing, the phase value is decreasing. Okay. And this is, of course, a linear phase response. Whenever we try to find the group delay, what does it mean? As you can understand from the phase response, there are different frequency components. It starts with the DC value and higher frequency and more higher frequency. So for a different frequency, we have different delay of the signal. For different frequency, we have different delay of the signal. Now, if I ask you, what does it mean by different frequency and different delay? Delay in which perspective? In the time domain or in case of phase? What kind of delay they are experiencing, this frequency component? Let's say we have omega 1, omega 2, omega 3. What kind of delay they are experiencing? They are experiencing the phase delay, and this phase delay is linear, isn't it? And whenever we are talking about the group delay, by definition, that is the delay with respect to omega. We have the phase with respect to d by d omega. We are putting a negative value, and we are getting the result is giving nd, which is 2. For our case, we are getting the value is 2. What does it mean by this 2 physically? Any of you want to share something to understand the group delay? What does it mean by the value 2 here? What is the group delay? First of all, what is the group delay in general?
Sir, every hello,
Yeah, you are audible. Yes.
sir, every frequency component is lag by a constant value which is 2, delaying by a constant value.
Constant value of two what?
The 2.
What is the unit of these two? Is that phase, or is that in the time domain, from the time perspective or the phase perspective? What is that? This
Sir,
group delay. Yeah. I can't hear you, Asif, at this moment.
yes, sir, I'm confused a bit.
Okay. Okay. Any of you would want to address something here? Because this is very important. Whenever we are talking about the communication, let me discuss in this way. That means you have some system. Whenever we are talking about any sort of filter, this can be also mentioned as H omega, Hn, all are the same. Whenever we are giving a signal Xn, which is a band of signal, you are putting it to the filter and you are getting the output as Yn. In that case, we are talking about, first of all, we'll talk about the linear phase. That makes your life easy. So I have already shown that this is a concept of the linear phase, where try to understand that this is at pi. So we are targeting, let's say we are targeting three frequencies, different frequencies. This is omega 1, omega 2, and omega 3. They are relative frequency. Still, we can understand that omega 1, omega 2, and omega 3. Omega 3 is the higher frequency. Okay, no problem about this. And let's say that this H omega is equals to -2 omega. Okay, so let that, this is the phase response. So from there, what is the group delay? The group delay can be mentioned as minus d by d omega with respect to omega minus twice omega, which actually produce what? This is 2. And now the question is, what does it mean by these 2 practically? Okay, so that is our main concern of this section. Okay, so try to be with me to understand the process. We have in Xn, what are the frequencies? We have omega 1, omega 2, and omega 3. Let's make this a kind of sequences here as well. To understand the portion, I'm drawing it with some references. Okay, this is omega 1, this is omega 2, and this is omega 3. I need to draw that. So let's say I'm drawing omega 1 with a frequency like this. This is omega 1. Omega 2 might have higher frequency. Maybe I can make double of that. Okay, so if I want to double of that, okay, let me take another color to understand the things. Maybe I'm taking the same amplitude. Okay, fine. And the last one, maybe it is double of the previous one. So that makes more higher frequency. One, 2, 3, and 4. So it's very easy to understand. This is 1 hertz, 1 hertz, this is 2 hertz, and this is 4 hertz. Okay, let this is 4 hertz. Okay, so ultimately higher frequency. Okay, now this line represents that it actually passes through a filter. So we are drawing what? Xn. How this Xn will be formed? By adding omega 1 plus omega 2 plus omega 3. That actually makes this Xn. In any part, if you have any confusion, please raise your hand and ask the question. Now, after passing it through the filter, what happens? Let's say this is the time t is equals to 0. That means t equals to 0. Whenever you are here, that is the time in the filter output. Now we are trying to find the yn. So at that very moment in the xn, whenever you are at this point, this is that point. You are at that point, this is that point, and this point means this point. Okay. Let me write another line. This is 1 sample period, and let me write another one. This is 2 sample period. Okay. And after that, let's say this is what? This is t is equals to, let's say t is equals to 4. So there are 4 samples. After 4 samples, you are getting the output. So this is t is equals to 4 seconds or something like that. You can assume anything. And now I am drawing the same thing here. The omega 1, and according to the diagram, so I'm doing it roughly. Okay, this is omega 2, and the last one might be difficult to draw, but still you can draw that. 1, 2, 3, and 4. This is omega 3. Need to be very, very clear that what kind of shifting you are getting in the output for yn. What is the delay you are experiencing? Can you tell me how many delays you are experiencing?
So 2 samples.
2 samples, exactly. This is 1 sample, one sample, that is 2 sample. That actually physically means that the group delay is 2. Whenever we are making that, the group delay tau is equals to 2. This is the physical meaning. That means all the frequency component means including DC value. If we have the DC, if we are focusing to this DC value, even this DC value is facing the group delay. What does it mean, the group delay? We have already found the group delay is 2. This group delay is for all the frequency. That is called the group delay. What is the group delay? Group means in this section we are all together is the group delay. If I have the delay to sign in the Zoom, you all should have the same delay, isn't it? Because you are already in the Zoom platform, but I haven't still signed in. Whenever I signed in, then you all are in. So that means we have the common group delay, and this is due to the linear phase. So you can understand this. Now we'll try to understand the linear phase. First of all, is that clear? What does it mean by this group delay physically? Is it okay? Any confusion?
No, sir.
Okay, it should be very much clear. Okay, now the second thing, how does it make sense that we have the same group delay 2s but or two sample. However, in the phase response, it is just changing whenever the frequency is also changing. How you can interpret that? So try to understand that whenever we are talking about this phase response, what is the phase for omega 1? What is the phase delay of the omega 1? Let's say this is the phase delay. So theta 1. For omega 2, what is the phase delay? That is theta 2. For omega 3, that is phi or theta 3. What does it mean? Now try to understand it. If I start this signal, the omega 1 signal from this point, what is the delay here? From the phase perspective, what is the delay? From the phase perspective, that is the phi 1. That is a phi 1. For omega 2, what is the delay here? That is phi 2. And what is the delay here for omega 3? That is a phi 3. Now my question is, which one is higher, phi 1, phi 2, or phi 3? And why? Phi 1, phi 2, phi 3. Which one is higher? Or all are the same?
No, sir. Phi 3 is higher.
Why? Phi 3 is higher with respect to omega 3, isn't it? Because this time frame, for this time frame, if I took that same time frame here, let's say this is the same time frame, what is the phase you are proceeding? Try to understand that. What is the phase you are proceeding? You are just proceeding almost twice pi. Let's say this is almost twice pi. For omega 2, what is the proceeding in between this? Let's say this is your phi 2. What is the proceeding there? This is only pi. Yeah. What is the proceeding here for phi 1? That is pi by 2, isn't it?
Yes.
Yeah.
Yes.
So then we can find that for omega 1, this phi 1 is equals to pi by 2, you can say. For omega 2, this is equals to pi. And for omega 3, that is equals to twice pi. And this is obvious from the diagram. That means if we think that from the time scale, what is the delay? From the time scale, what is the delay between the starting point? How we define this starting point? This is the starting point of this, because signal is passing through all the time. Are the signal waiting for up to the end of the sample? No, they are passing through the filter. All the signal. Basically, the xn is a combination of these three signal. And what is yn? Yn is also combination of these three signal. Then if you want to get your yn, if you want to reconstruct the yn, or you can say xn, how many seconds or how many samples you need to delay your system?
2 samples.
2 samples. And that is true for all the frequency component, and that's why this is called group delay. If you do not stay for 2 seconds, first 2 seconds, then what happens? There will be a 0 value first, and then afterwards maybe you are getting your signal like this, isn't it? So that's why we need to actually delay these 2 samples, and this is called the group delay. I believe you understand the everything about the group delay. And that is a fact. And unfortunately, the books and the video lectures, they are not defining the things with the example. They are just writing the equation. Okay, now this is all about linear phase. You can understand the thing. And there is no problem, because after 2 samples, you can all add omega 1, omega 2, and omega 3. And okay, fine, you are getting yn, which is equals to your xn. So there is no distortion. You are getting exactly the same signal back. Okay, fine. Now let me draw a nonlinear phase response. This is, let's say the rate of change is higher, rate of change is average, and the rate of change is very low. I'm writing 3 sections. Okay, might be a little bit more higher, like this, and like that. Okay, so the points can be defined. So these are the points we are just turning out. So for omega 0, this is for omega 0, omega 1, and this is for omega 2, and this is for omega 3. So you are not getting a single group delay here, isn't it? For the section, let's say I'm putting the point 1 and 2, and 2 and 3, 3 and 4. In the section 1 to 2, the group delay 1, in case of 2 to 3, there is a group delay 2, and from 3 to 4, there is a group delay 3. And if I write the sequence, of course, tau 1 is definitely higher, because the rate of change is higher than tau 2 and then tau 3. The group delays are different. The group delays are different. What about the phase? Of course, they are different. In case of linear phase as well, you have already found that the phase are different. Okay, so this is your xn, as we have found previously. Okay, what I have shown earlier. Okay, you can imagine that. And in the right side, let me draw omega 1, omega 2, and omega 3. This is the starting point. This is your t is equals to 0. Now, what we are expecting, let me write in this way. This is 1 sample delay. This is 2 sample delay, 3 sample delay, 4 sample delay. Let me do like this. What about omega 1? The delay, group delay, let me give some number. The tau 1 is like 4. Tau 2 is equals to, let's say, 2, and tau 1 is equals to 1. Try to understand the thing. So how you can got this number? From analyzing the phase response. So for omega 1, this for omega 1, what is the delay? How many samples delay they are experiencing? 4 samples delay. So 1, 2, 3, 4. 4 samples delay, and after that, the signals appear here. Good. This is okay. Okay, just making some boundary over this. Is that okay to you, everyone? If you have any problem, I can repeat the things from the starting, because this is my main motivation to make you understand the linear phase, non-linear phase, and group delay very efficiently, so that you never can forget this. Okay, even if you want to forget the things, you will not forget the things. Okay, is that okay? Omega 1. The 4 samples delay. Yeah, okay, fine. For omega 2, where it will start?
2 samples.
After 2 samples, 1 sample, 2 sample delay. And then, of course, that carries a higher frequency. Okay, let me take the boundaries over there. So higher frequency, just approximately, I'm writing like this. There'll be 2 frequency. Let me 1, 1, 2. Okay, this is omega 2. For omega 3, the last one, omega 3, what is the delay?
1 sample.
1 sample delay. Let me give the boundary here. 1 sample delay. So 1, 2, 3, 1, 2, 3, and 4. 4 hertz it was. This is omega 3. And now you can understand the thing. Due to this non-linearity of this kind of phase, non-linearity, this is the non-linear phase. Okay, I have shown it like this. And for this kind of non-linearity, what happens here? Yn. If you add the things, will that work? Can you retrieve back your xn?
No, sir.
No, that makes a problem, definitely. What you need to do, you need to delay the omega 2 more, you need to delay the omega 3 more in such a way so that the group delay is again 4, if you can make it. If you can make that, then it can happen. You understand my point? Now, what are the delays we need to put? We need to put 2 delays, more 2 delays for omega 2, more 3 delays for omega 3, so that all the signals actually experiencing 4 delay. Otherwise, if you add all the signals like this, then what happens? You are getting some distorted xn. You are getting some distorted xn. And the distortion is known as phase distortion. The distortion is known as phase distortion. And this is very, very damaging for the system. Now, what we can do, after getting this kind of signal, this is the output of a which kind of filter? This is the output of a which filter? FIR filter or IIR filter?
IIR filter.
IRR filter, because IRR filter gives this kind of non-linearity. So you have your xn given to a IIR type filter, and you get something distorted xn. You are getting some distorted xn. So we are not accepting that. Now what we can do, we can put this distorted signal to another IIR type filter so that the group delay can be a constant 4. What does it mean? It means that, try to follow this. For omega 1, to counterbalance this part from 1 to 2, what we can do, we can give very low rate of change. We are designing now. For 2 to 3, we can make the actual one, whatever the delay there. And for 3 to 4, we can give, let me draw the things again, like that, up to 0.3. Okay. And from 3 to 4, we are having very high rate of change. So again, we are dealing with 3 points. One is very small rate of change, medium rate of change, and high rate of change. Now, what does it mean? They are doing the opposite. They are now doing the opposite type of delay. What does it mean? Now the new filter, for the new filter, the tau 1 may be given the delay 1 sample. You can understand because the rate of change is low. So they are giving 1 sample delay. The tau 2 give, let's say, 3 sample delay, tau 2, because it's now higher, and tau 3 gives 4 sample delay. This is new tau 1 given 1 sample delay, new tau 1, tau 2, tau 3 from this new IIRR type filter. So they are giving 1 sample delay, 3 sample delay, and 4 sample delay. So altogether, omega 1 experiencing how many samples of the delay? Previously it get 4 samples delay, and now it gets 1 sample delay, so 5 samples delay. What about omega 2? Previously it experiences 2 samples delay, and now 3 samples delay, so it is also 5 samples delay. Similarly, for omega 3, previously it experiences 1 sample delay, now 4 samples delay, so again 5 samples delay. So at the end, what happens? Omega 1, omega 2, and omega 3 all are experiencing 5 samples delay. And the structure can be written like this. This is your xn given to a filter, IIR type filter. Whenever we are talking about tau 1, tau 2, and tau 3, they are experiencing the delay of 4 sample, 2 sample, and 1 sample. And given to another IIR type filter, where we just want to do what? We want to rectify, neutralize this delay. So now this tau 1, tau 2, and tau 3. So tau 1 experiencing 1 sample, tau 2 experiencing 3 sample, and tau 3 experiencing 4 samples delay. So at the end, what we are getting our exact xn. There is no distortion. Here we are getting the distorted xn. Now the things are pretty simple. Here basically we have done our filtering job. Here we are done our filtering job. So this IIR type filter basically works for filtering. And this IIR type filter works for restore the group delay. So this IIR filter will pass everything. That will pass everything. And that's why this is called all pass filter. That will pass everything, all the frequency. That will not rectify anything, but it will only restore the group delay in such a way that the total group delay, group delay should be a constant number. For our case, that is 5. So at the end, this combination should works like a what kind of filter? This combination should works like a
FIR filter.
FIR filter. So if you allow me to draw 2 filter, let's say the phase response, okay, and the other, this is for one, and the other one is basically the in reverse the pattern. They will produce the reverse of the pattern, and altogether whenever you are adding those they have produced a straight line like this. So this one is from IIR filter actually, and this one from all pass filter, and it looks like FIR type filter, where the group delay is a constant value, ND, the constant. So that is the whole story of group delay. Why we need the all pass filter? Definitely you can understand why we should need. And this is mandatory. Whenever you are using a IIR type filter for a particular signal processing technique, of course, you have to have the all pass filter after, before ending the filter sequence. Otherwise, you are facing what kind of problem it will produce? It will give us the phase distortion, which is not acceptable. That is why sometimes people are using only FIR type filter. There is a problem in the IIR type filter, though there are some advantages. So whenever you are working with a very, I should say, sensible signals processing for like biomedical engineering or space science, then people are always using FIR type filter, because this kind of phase distortion may work, even though you try to design a better all pass filter, but it might make, still there might some problem. Okay, so in the next class we'll talk about this problem, inshallah. Okay, any question? We have only 1 minute, so no need to ask about the question at this moment. So thank you very much for your participation.